So to sort of recap the point and graphically sort of present our previous argument, right? Given this normal distribution, given these are the possible values that are observed from this variable, and on the y-axis we have the probability level, right? So our question is, what is the probability of observing a precise value? Okay. So instead of using, the height method, right? So instead of saying, what's the height of this point, we're looking at, first of all, a method where we'll determine a very small range or band that includes our target value. Okay. Well, here is not very narrow, but for illustration purposes, let's say this is a very narrow band that includes 4. Okay. And then the next step, actually, to find out the probability of observing a value 4 is to calculate the area of the band under the normal curve, is to mathematically find out what is the area of the shaded part, right, between the curve and the x-axis and also within the two boundaries, right? Here's one boundary, here's the second boundary. So what is the area of this shaded part? And the area of the shaded part will be the probability of finding 4, right? Or technically finding the very narrow band that contains 4. Okay? And the probability is the area of the shaded part. Okay, so this is a little counterintuitive, but for now, let's remember this sort of conclusion. So to go back to our example, right? So then under this distribution or any continuous distribution, right? The probability of observing 4 is made to equal the probability of finding any value that's within this very, very small range, right? So it could be 3.99999 or 3.0005, right? That's okay. We'll consider the probability of observing 4.00005 equivalent, right? Enough to the probability of observing 4. Okay? So that gives us actually a way to do more than finding out the probability of identifying one single value. So now we can actually say, well, then can we do the same thing to find out the probability of observing a value that's larger than 4 but smaller than 5? Well, of course, right? Because just now we saw that the way of finding the probability of observing a particular value is by specifying a very narrow interval that contains the target value. Then of course we can find out the probability for observing any value that's within an interval. Easy enough. We'll put a boundary at 4, we'll put a boundary at 5. So as long as we can calculate, which we can, the area of this part, right, the shaded area, the shaded part, right, the area of the shaded part, that will give us the probability of observing any value that's larger than 4 and smaller than 5, right? So the area of this part, the shaded part, will be the probability of observing any value, right? Any x that's larger than 4 but smaller than 5 within here. Okay? So that's the probability. Okay, now let me ask you, given this distribution, then what's the probability of observing a value that's larger than 5 here or smaller than 4? How can we do that? What's the probability of finding a value from this sample, right? Given this distribution that is larger than 5 or equal to 5 or smaller, or no greater than 4. Okay? It's actually very easy, right? You should pause now and think about it before I announce the answer. The answer is the probability of finding a value that's no smaller than 5 or no larger than 4 will be the difference between 1 minus the probability of finding any value that's within this interval. Okay? It makes sense, I hope, to you very quickly that why we need to use, why we can subtract this probability from 1, because we said in the previous class that the total area under this curve, right? The total area under this curve is 1, because the total area under this curve represents the probability of observing all possible values of this variable. Then the probability of observing all values of variable, well, that's certainty, right? So certainty, mathematically, it's 1. So in other words, the total area under this curve is 1, and if we already know the shaded part, the area of the shaded part is this, then of course the area left, right, from left within this curve, right, from this shaded part will be 1 minus the probability of observing any value that's larger than 4 and smaller than 5, right? So it will be this part, right? It will be the area under the curve bar the area of this part. Then of course, right, we use subtraction. Well, similarly, right, we can calculate the probability of observing a value that's greater than a particular value. What should it be, right? So that's a range. That's also interval. That means, from 4 to all the way to 7, actually, right? Because 7 is our upper bound, right? But we don't have to specify 7 here because, this curve will only extend to 7, right? Well, it's not precise here, but you can imagine there should be a cutoff line here, right? The curve should be like this, right? Ends at 7, okay? So then, right, what we also need is an interval, right? So it turns out that 4 is the mean here. That is, it will, if we impose a center line, it will run through 4, okay? So in other words, to find out the probability of observing a value that's greater than 4 is just to find out the area of this part, right? From 4 all the way to 7, okay? So it will be actually 0.5 because this is actually half of this bell-shaped curve, right? So if the total area under this curve is 1, and if 4 happens to be the mean, right, then of course, if we impose a center line, that would divide this curve into 2 halves. And of course, right, then it will be 0.5, right, as the chance of observing any value that's greater than 4. Okay, so here is, P, the probability of observing any value that's greater than 4 is 0.5, provided that these values are normally distributed and 4 is the mean, right? It's also the median, it's also the mode, okay? Well, 0.5 will also be the probability of observing a value that's smaller or no greater than 4, right? Because that's 1 minus 0.5, that gives you 0.5. Okay? So the essence, in other words, in more general terms, of finding, any particular value, any, an interval of values under a normal distribution or any continuous distribution is to specify a relevant, interval, right? If we are looking for the probability of finding a particular value, an exact value, then we specify a very narrow band across it, that contains it, and our job then is to, figure out, or here, right? So let's say 3 is here. Then to find out the probability of observing 3 under this distribution, then we just specify a very narrow band that will contain 3, and then we'll calculate the area, right, of this band. So the area of this band will be roughly the probability of observing 3. But if you want to say, well, what's the probability of observing any value that's larger than 1, smaller than 2? Easy, right? It will be the probability, it will be actually the area of this part, right? Then you say, well, what's the probability of any value that's greater than 2, right? Then it will be all the way, right? The area of the part, to the right of 2, and the probability of any value that's smaller than 2 will be the area of the part that's to the left of 2. Okay, easy enough, I hope. Okay, so so far we have actually sort of worked out the general principle or general way of finding out probabilities of observing some kind of value if the value follows a normal distribution. Mathematically, there are many ways to do that, but for the purpose of this class, we'll be focusing on what we call the empirical rule. Empirical rule is a approximate way of finding out probabilities. The probabilities that obtained from using the empirical rule will not be precise or exact, but it's close enough, right? And for this introductory class, we consider the empirical rule a good enough method of working out the probability of finding or observing some kind of value if the values follow a normal distribution. Okay, so here is the empirical rule, what the rule says. The first statement of the empirical rule says, given a normal distribution, okay, so there will, the probability of a score that falls within 1 standard deviation around the mean, right? Here is 1 standard deviation above the mean. Here's 1 standard deviation below the mean, right? So it says the probability of any value that falls within this range is about 68%, or the probability is 0.68, or the area, right, of this shaded part bound by 1 standard deviation above and below the mean is 0.06. Okay, that is, for any value that's larger than or smaller than 1 standard deviation around the mean will be 0.68, right? Okay, the second statement of the empirical rule says, for any value that falls between 2 standard deviation below or above the mean, right? Any value that's within this interval, right, is about 0.95, right? That is, there are 95% of the chance that we can observe a score that will fall within this interval. Okay, 2 standard deviation around the mean. So any value, right, that's greater than 2 standard deviation below the mean or smaller than 2 standard deviation above the mean, the probability of observing this value is 0.95. Lastly, it says, the empirical rule says, for any value that's within 3 standard deviation around the mean, the probability of observing this value is close to, but not yet 1, right? It's 0.99. That simply means almost all values, right, will fall within 3 standard deviation below and above the mean. There are a few values that are not included, but the majority of values will be within 3 standard deviation above and below the mean. Okay, So we have, in other words, 99% of the chance to observe a score given this distribution, right? That's larger than 3 standard deviation below the mean and greater than 3 standard deviation above the mean. Sorry, it should be 3. Okay, it should be 3. Okay, right? Exactly. Okay, so this is the 3 statements will constitute what we call the empirical rule. Okay, but then how do we use it? So imagine, right? Angie surveyed 500 people on their attitudes toward gun control on a 7-point scale, right? And then we know from calculating, from working with the numbers, uh, that these 500 people, the average score of these 500 people is 4, and the standard deviation of this sample value is zero point 0.5, right? We further assume that the scores, these 500 scores, follow a normal distribution. I can ask about how many people in a sample had an attitude score that's greater than 3.5 and smaller than 4.5. Okay, so given all these sort of conditions, we can roughly plot the distribution, right? First of all, it's normal, okay, and then we know that the mean is about 4 and standard deviation is 0.5, right? And then we want to know about how many people in the sample had an attitude, or scored, about how many people in the sample scored between 3.5 and 4.5. So first of all, we should find out where are 3.5 and 4.5 on this distribution. That is our first step. We should establish the cutoff values, because the cutoff values will allow us to establish boundaries, right? To determine, to help us determine the area of a shaded part, but then we need the boundaries to first of all specify the part whose area we want to find out. Okay, so that translates to the question of where are 3.5 and 4.5 on this distribution, or on this axis, right? This axis represents values, right, of the variable. Okay, what do you think? Where should they be? Okay, to find out where they are, well, actually, you should already see that 3.5 should be around here, right? And 4.5 should be around here. Okay, but to be more precise, we'll need to calculate their z scores. The z values corresponding to 3.5 and 4.5. Okay, should be easy, right? If we recall, z values equals to the target value minus the mean divided by standard deviation. Okay, so for 3.5, we know that it's the mean of 3.5, or the sample from which 3.5 is drawn, is 4. Okay, and then we divided this difference by standard deviation, which is 0.5. Okay, so it's negative 0.5 divided by 0.5, so that's negative 1. Okay, and we calculate the second sort of z value, that will be 4.5, right, minus 4 divided by 4.5, so that will be 0.5 divided by 0.5, that's exactly 1. So that means 3.5 is exactly one standard deviation below the mean, and 4.5 is exactly one standard deviation above the mean, right? Because the difference here is zero point 0.5 and exactly one standard deviation. The difference here is zero point 0.5, which is also exactly one standard deviation. So 3.5, 4.5 are exactly one standard deviation below and above the mean. So this will be the part whose area we're going to find out. And by finding out the area of this shaded part, we should be able to know the probability of observing any value that's within this interval, right? So the last step, once we figure out, the number of standard deviations that these values are around the mean, we will be able to apply the empirical rule. Okay? Because we just said, right, the first statement of the empirical rule says there will be about 68% of values that will fall between one standard deviation above around the mean. Okay? So this is it. We know that from calculation that 3.5 and 4.5 are exactly one standard deviation around the mean. And according to empirical rule, there should be 68% of the scores that will fall within this interval. So it will be 0.68 times 500. That will be 500 times 0.68, that's 340. So there will be 340 people who will score between 3.5 and 4.5.